Dear students, I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. Today I will discuss London equations. These London equations are important in superconductivity. In my previous lecture, I have derived two London equations. First London equation is variation of current density Js with respect to time. It has a value ns e square capital E upon m. Capital E being the electric field. Ns is the density of superconducting electrons. The second expression is curl Js is equal to minus ns e square B upon m. B is the strength of magnetic field. These two expressions, they are derived by using a two-fluid model in which we have assumed that superconductor comprises of two types of electrons, superconducting electrons and normal electrons. If the density of superconducting electrons is Ns and the density of normal electrons is Nn, these two parameters, these are dependent on temperature. This graph shows the temperature variation with density. Graph is plotted in the temperature range 0 to Tc. When temperature is 0, here we can see that density of superconducting electrons is maximum, and at T equal to 0, Nn is 0. And as we reach up to Tc, it can be shown from the figure that Ns is 0 and all electrons are normal electrons. That means material has been changed from superconductor to normal. In the intermediate region, both electrons are contributing. But as we know that for superconductors, electrical resistivity is 0. Hence, most of the electrical current will be because of superconducting electrons. Hence, we have used the density of superconducting electrons only. We have ignored normal electrons. Now, these equations are further modified. For this modification, I am using Maxwell's fourth equation. Maxwell's fourth equation is curl B is equal to mu 0 Js plus del D by del T. Here del D by del T, this denotes the variation of displacement current D with respect to time. I am assuming that fields are varying slowly with time. So this term can be neglected. So del D by del T equal to 0. So we are only left with the term mu 0 Js. Equation becomes curl B is equal to mu 0 Js. Now I am taking curl of this expression, taking curl on both sides. This side will become, left hand side will become curl B and right hand side will become mu 0 curl Js. Now using the identity of curl vector, I got curl B as grad div B minus del 2B is equal to mu 0 curl Js. Now since divergence of B is 0, first term in this expression will be equal to 0. So this equation becomes minus del 2B. This is equal to mu 0 curl Js. From here I can get the value of curl Js to be equal to minus del 2B upon mu 0. I have already derived curl Js from London expression. This was second London equation. This shows curl Js to be equal to minus ns E square B upon M. So first, using the London equation, I have derived curl Js, and secondly, using the fourth Maxwell expression, I have obtained curl Js. Now, equating both these curl Js, I got the value of del 2 B to be equal to mu 0 ns E square upon M B. Substituting this value, which is a constant factor, as mu 0 is constant, density of superconducting electrons at a particular temperature will be constant, E square and M are constant. I have put on this value to be 1 upon lambda L square. I got the second order differential equation del 2B is equal to 1 upon lambda L square B. This lambda L, which is constant, is termed as London penetration depth. Now, what this equation means, in order to find out its complete solution, I am considering a superconductor which is occupying a space on the positive x-axis. This I am showing this by diagram. Here we have taken a superconductor which is on the positive side of x-axis. Now, on the surface of this superconductor, parallel to the boundary, I am applying a magnetic field of value V0. According to this expression, which is a second order differential expression, solution must be Bx is equal to B0 exponential minus x upon lambda L. This is the solution of second order differential expression. Here B0 is the amplitude which I have applied on the surface of the specimen. This shows that magnetic field decays exponentially over the surface thickness, which has a value equal to penetration depth. Penetration depth being the lambda L. This lambda L has a very small value of the order of 10 raised to power minus 6 to 10 raised to power minus 5 centimeter. Hence, because of the small value, lambda L in this expression has a very small value. Bx is in almost all superconductors is almost 0. But this exponential decay, which is shown here, it is showing that it is exponentially decaying from maximum at the surface to the interior of the specimen. It is exponentially decaying as the value of x increasing. But according to Misner effect, B must be completely 0 inside the superconductor. These London equations, they do not replace the Maxwell equation, but they are the additional conditions which a superconductor must follow. This penetration depth depends upon temperature. As T approaches Tc, we know that the material will become superconductor at Tc, hence Ns will approach to 0. And at low temperatures, it has been found that this London penetration depth is independent of temperature and it has a constant value equal to lambda 0. Lambda 0 is dependent on the material. Magnetic field variation with distance is shown in this graph. Lambda variation with temperature can be expressed by a relation of the form lambda upon lambda 0. This equal to 1 minus T upon Tc raised to the power 4. This whole to the power minus half. We know that density of superconducting electrons is also dependent on temperature. The density of superconducting electrons with temperature depends according to the relation Ns equal to N0 1 minus T upon Tc raised to the power 4. Here Tc is the critical temperature, N0 is the density of electrons at absolute zero, and similarly here lambda 0 is the London penetration depth at absolute zero. Now these two expressions are used to find out the value at two different temperature range. I am finding the value of concentration Ns at T equal to 0 and at T equal to Tc. Similarly, I am finding out the London penetration depth at two values T equal to 0 and T equal to Tc at T equal to 0 Kelvin. At T equal to 0 Kelvin, putting T to be 0, Ns will be equal to N0. This means at absolute 0, the total concentration will be N0 being the total concentration. At T equal to 0, the total concentration will be equal to the density of superconducting electrons. Now I am using T equal to 0 in the London penetration depth formula. I got lambda to be equal to lambda 0. Now taking the range T at the temperature T equal to Tc. Putting T equal to Tc in this, Ns will be equal to 0. That means at T equal to Tc, density of superconducting electrons is 0. Hence all electrons will be normal. That means material has transformed from superconductor to normal. Now I am putting T equal to Tc in this expression. Substituting the value of T to be equal to Tc, I got it to be equal to infinity. That means at T equal to Tc, London penetration depth is infinite. This means that magnetic field penetrates totally inside the superconductor, which means that material has transformed to a normal material, and by placing a normal material in a magnetic field lines will penetrate inside as well as outside. Misner effect is followed for a superconductor only. That means Misner effect states that for superconductor B must be equal to 0. These are two basic London equations which were derived to determine the density of superconducting electrons when they are placed in magnetic field. Thank you for watching.